The second case, dt by dz environmental, which is environmental lapse rate is greater than dry adiabatic lapse rate. So when we draw the air parcel, which is the dry adiabatic lapse rate, if its increase, if it is going up and the temperature inside the air parcel is less than environmental lapse rate, which is the atmospheric condition surrounding it, then the temperature condition is said to be unstable. There are chances for rain, heavy winds. Okay, so ALR and ELR, and if ELR is greater than, that is the lapse rate of the surroundings, the temperature of the surroundings is greater than adiabatic lapse rate, or the temperature decrease in the surroundings of an air parcel is greater than the temperature decrease of the air parcel within the system, then that condition is called as unstable. Okay, here environmental lapse rate would be higher than or greater than dry adiabatic lapse rate. Okay. The third condition is where environmental lapse rate is less than dry adiabatic lapse rate. Okay. So in this scenario, the air parcel, the temperature decrease in the air parcel with elevation is greater than the temperature decrease in the surroundings. I repeat, in the third condition, when environmental lapse rate is less than dry adiabatic lapse rate, the air parcel of concern in this box, when it goes up, the temperature within it decreases to an extent. For example, it decreases by about 5 degrees Celsius. Okay, and the temperature decrease in its surroundings when it goes by up is about only 3 degrees Celsius. In this scenario, the DALR is greater than ELR. Okay, or we can write it as ELR is less than DLR. In this scenario, this situation, the condition is called as stable. In this condition, the atmosphere is perfectly stable. It is more stable than our neutrally stable condition. So the three cases are: first case, ELR equal to DLR. The second case, in which second case, ELR greater than DLR. And the third case is ELR less than DLR. The first case is neutrally stable. Second case is unstable. And third case is stable. So in this neutrally stable case, winds can happen if other scenarios change, like for example wet adiabatic lapse rate. Okay. In the second scenario, the temperature is unstable and winds can happen. Storms can happen. In the first case, storms and winds won't happen normally, but if wet adiabatic lapse rate comes into the scenario, winds and storms can happen. And the third case, even if wet adiabatic lapse rate comes into the equation, there is a chance that the atmosphere will continue to be stable. and that is why the third condition is called as stable. In this three cases, the second case is called as super adiabatic condition because of super adiabatic condition, because of the instability that arises due to the second case. Okay. There is a fourth case where WALR, which is wet adiabatic lapse rate, is greater than DALR. In this scenario, rains can happen. Rains will happen, and if the moisture content is higher than a particular limit, there will be torrential rains and there will be violent storms. Okay, this is the fourth case. We will start with Gaussian plume model. In the Gaussian plume model, it's usually used to determine the plume height of a factory. What is a plume, or what is the relationship of Gaussian plume model with the factory or industry? Consider this as a factory, okay, and this is called as chimney, and this is called as plume. Okay. We will start with Gaussian plume model. Gaussian plume model is used to determine the direction, speed and the dispersion of a plume. What is a plume? Plume is nothing but the smoke, the concentration of smoke that is coming out of an industry. Consider this as the factory and this is the chimney, okay, and the gas is coming out of it is called as plume. The smoke coming out of the factory is called as plume. Okay. So in the Gaussian plume model, we will determine how we can predict the direction, speed, and most importantly, the dispersion of the smoke plume that is coming out of a factory's chimney or a stock. Consider Z1 is the elevation from the ground level to the plume, okay, and the elevation at the ground it is Z2, and the elevation from where the plume is dispersing it is Z1, okay, and the wind speed at the ground level it is called as U2, and the wind speed at the plume level is called as U1. So Z1 by Z2 equal to U1 by U2. So Z1 by Z2 is equal to U1 by U2. So this is the equation that we assume in the Gaussian plume model. In this, there is a dimensionless factor known as P, which we normally put as a superscript for Z1 and Z2. So the atmospheric conditions can be defined by this dimensionless quantity known as P. Okay, so the P factor, if we determine the P factor, we can determine the conditions of the atmosphere. We can determine the conditions of the plume, the dispersion of the plume. So in the condition A, the P value is 0.15, which means the atmospheric condition is highly unstable, very unstable. Okay, In the B condition, the P factor is again 0.15, but the description is moderately unstable. And the C condition, the P factor is 0.2 and the condition becomes slightly unstable. And in the D condition, the P factor is 0.25 and the description of that condition becomes neutrally unstable. And in the E, from E onwards, the P factor is, the value of P is 0.4 and the condition becomes stable, okay, or slightly stable. And in the F factor, in the F condition, the P factor, the value of P becomes 0.6 and the description of that condition is stable. So this is how we determine the stability of a plume and the atmospheric condition, and how we can predict the plume dispersion, the smoke dispersion from a plume using Gaussian plume model. There are other aspects in this regard also. We'll discuss about that in our next video. Until then, bye.